This video covers a little bit of material from Chapter 4 of your Analytical Chemistry textbook. Specifically, we're going to talk about some statistics definitions and then some simple statistical tests you can do on your data. Doing statistical tests using your data from Chem 300 lab can help you figure out what the error is in your result and therefore what precision you should report your answers to. You can also figure out the probability that the value that you have measured is actually the true value. To do this, you need to you're going to do multiple trials and you need to calculate the mean of those trials, which I assume you already know how to do. You can then calculate the deviation from the mean for each of your trials. And this deviation from the mean, the spread of your results, is going to allow you to calculate a couple more things. You can calculate the average deviation from the mean, which is calculated in the same way you would calculate any average. You can also calculate the relative average deviation, which is as the name suggests, a relative error. More commonly, though, you'll use that deviation to calculate the sample standard deviation. In the denominator, under the square root sign, you see n minus 1, and so this is the number of degrees of freedom for your measurement. N is the actual number of trials, number of measurements that you take. Since you've calculated an average, you've removed a degree of freedom, and so you're dividing by n minus 1, the number of degrees of freedom. If you square the standard deviation, you get what's known as the variance. In practice, we don't normally do that. We just calculate the standard deviation. S is designated the sample standard deviation to distinguish it from sigma, which is the population standard deviation. The population standard deviation applies as you do an infinite number of trials. We say infinite by definition. In practice, it's just a large number. In either case, it's much larger than what you're going to have time to do in Chem 300 lab. The relative standard deviation is calculated the same way as the relative average deviation from before. This is the one, though, that we're going to more commonly do, again, because we're usually going to calculate a standard deviation. The reason we calculate a standard deviation is because it has applications to a bunch of other statistics that are more descriptive than just the average deviation or standard deviation. These statistics assume that if we do a measurement a bunch of times, the results that we get are going to lay on what's called a Gaussian distribution, or you may have heard it called a bell curve. This is a plot of probability versus measurement distance from the true value, and it takes the shape of this little bell curve. The true value is the horizontal line on this graph. In the equation below, it's represented as mu. And then each of the individual measurements are x sub I. The width of this curve is dictated by sigma, the population standard deviation. If we can reasonably assume that our samples lie on that Gaussian distribution, statistics become pretty easy. But we need a big number of samples for that because, if you remember, that equation used the population standard deviation, not the sample standard deviation. So if we want to use a small number of data points to compare our average, x bar, to the true value, mu, we can use what are called t-statistics. And when we do this, we can calculate a confidence interval using this expression t times s over square root of n. And what that tells us, it gives us an uncertainty range in which the true value somewhere occurs. All right. In this case, S is our sample standard deviation, N is the number of measurements, and T is a number. And where you get that number is in your textbook, table 4.2. It depends on the number of degrees of freedom, so the number of measurements you do minus 1, and it also depends on the confidence level that you want your confidence interval to be. So you can say I am 99% confident, or 95, or 90% confident. If you say you're 68% confident, you're talking about one standard deviation. More standard deviations give you a bigger range, but then you get more confidence as well. So that's one use of this thing that's called student's t. Another way to do this is to use student's t is to analyze repeated measurements to compare results of replicate measurements over and over to see if the individual results correspond to one another, testing the precision of your method. You can also compare measurements made from different methods. In any case, the t-test is going to allow us to make a determination. Are our results statistically similar, or are they statistically different? We can compare our measured results with a known value, which is sort of the most useful thing to do if we have a known value. What we can do is say, okay, we measured our sample 10 times, and we know that the answer should be X, and we got Y. And so we can use our t-test to determine whether X and Y are statistically similar or statistically different. In a different case, we may have results of two sets of measurements made with the same method. So we do our measurement once, maybe 6 times, and we go away, come back the next day, and do it again 6 times using the same method, using the same sample. We don't have a known true value in this case. We're just testing one sample over and over. But we can see if our method is giving us the same answer every time using this kind of t-test. And so what we do is calculate a pooled standard deviation using the equation there, and calculate a t-value using sort of a combined, we're combining sort of two instances of that equation for t, the confidence limit that we saw previously. So we calculate t, we compare it to the tabulated t-value, and if the calculated one is bigger than the tabulated one at whatever confidence level we want, doesn't have to be 95%, then we would say the two results are statistically different. We can also compare measurements from different methods. So we would do this, for example, if there's a reference method that's used to test some analyte level in some sample, and that's the commonly done way of doing things. And let's say we invent a different method and we want to see if it's as good as the accepted method. We would use what's called a pair t-test in this case. So we would calculate the standard deviation using the equation shown there, and then we would calculate a t-value using the standard deviation of the differences and the average deviation. And then do the same comparison as before. Compare our calculated one to the tabulated one. We can also use students' t to design a sampling protocol to tell us if we want a given uncertainty level, how many samples should we analyze. So we go back to our original t equation, but we rearrange it to solve for n. That's what we care about, is how many samples should we analyze. We also substitute mu minus x, or mu minus the mean. This is just a measure of error. How wrong is x bar compared to mu, the true answer. All right. S is the standard deviation for sampling, so this needs to be established before we start. We need to know the precision of our method. E is the desired uncertainty in the measurement. If we want to say we need enough samples to be within 1% or 0.1%. What we do, this is an iterative method that we're going to use. So we use the t-value for an infinite number of samples and put in all of our values and calculate n. And n is not going to be infinity. It's going to come out to be something smaller. And then we would use the t for that new n and solve again, find another n, use a new t, use a new n, and keep solving for n until the values start to converge on one number. That number is the number of samples that we should do. All right, finally, a different kind of statistical test that we can do is one for rejecting outlier data points. And this is something that's going to come up in your lab. So we'll say you do 4 titrations, and one of them is, the answer is just way off. You calculate your molarity or whatever you're calculating, and it's way off. And you say, okay, did I do something wrong? Is this just too much random error in this one sample? Is there systematic error? Whatever. So the way that we do this is to use what's called the Grubbs test to reject the data point. So we take our questionable value minus x bar and divide by the standard deviation, and we compare that g value to a g table, just like we did for the t-test. All right, and if the calculated value is greater than the tabulated value, we say they're statistically different, and we reject the data point. In either case, whether you're using Q-test or Grubbs test, you need to use common sense. And what I mean by that is that if you spilled half of your sample and you got the wrong answer, well, you know why you got the wrong answer. You spilled half of your sample. So you just reject that data point out of hand and say it was wrong. There's a technique called doing a burn trial for a titration where you intentionally miss the endpoint just to see where it is, to make your next titrations go quicker. If you're doing a burn trial, you know you've intentionally missed the endpoint, and so you can reject that data point out of hand. So if you can't find an explanation for why your number is wrong, use a statistical test. If you can, then use that.